Hello, Marts here. This video is about conditional probability and about independent events. I'll say, so what's conditional probability? So we're talking about, say we have two events, A and B. So this is the probability that A will happen given that B has happened. And we write that as the probability of A given B, like that. And to find this, we have to remember that to find the probability of something, that is how big the part is. So the part here being, for example, the number of possible outcomes that is the event A, divided by the whole. That is all the events that could happen. To get a formula for this, we can reason ourselves a formula for that using a Venn diagram. Okay, so say we have a situation like this. We have two events, A and B. We'll say the probability for A to happen but not B, this part here, is say 0.2. And say the probability that A and B happens, so that is the intersection, is say 0.3. And say that the probability that B happens but not A is 0.4. That also means that 0.4, 4, 5, 6, 7, 8, 9. Okay, so the probability that neither would happen would be 0.1. Okay, so we know that the probability for A to happen equals to 0.2 plus 0.3 is 0.5, right? And we know that the probability for B to happen is 0.3 plus 0.4, 0.7. Okay. And now say we want to know what is the probability for the A to happen given that B has happened. So the probability for A to happen given that B has happened. We should try to make a formula for that and then calculate that for this particular case. And to figure that out, we can yet again resort to our Venn diagram. And this is event A and event B again. And B has happened. We know that we are here. Right. We know that that part is where we are. B has happened. Now we ask how big the probability for A to happen. And for A to happen, then you must be in here. If B has happened, the only possibility is that we are in here now. If A happens and B has happened. And yet again, we resort to this formula and say, okay, what is the probability for this? That is really how big is this compared to that? How big part is this of that? And this part here is the probability for A intersection B, which can be thought about the probability that A and B has happened, right? Divided by, that is this part there, right? Divided by the probability for B to happen. And that will be our formula. So in this case, the probability for A to happen, given that B has happened, will be the intersection, which is 0.3, divided by the probability for B to happen, that was 0.7, so that will give us 3/7. So now we have calculated the probability for A to happen given that B has happened. And we have reasoned ourselves to this formula. And I think it's easy to use the formula if we understand the reason why it looks like it does. Okay, I hope this clarifies a bit or helps a bit. Okay, let's look now at independent events. So two events A and B are independent if the probability for one of them to happen doesn't influence the probability for the other one to happen. So, in other words, if A and B are independent, then the probability for A to happen, given that B has happened, must be equal to the probability for A to happen. It shouldn't matter if B happens or not, the probability of A will stay the same. And the same thing, we have that, this is very important, and the same thing, I have that probability for B to happen, given that A has happened, must be the same as the probability for B to happen. Nothing changed. No change here. B doesn't depend on A, so the probability for the B to happen, it doesn't matter if A happened or not. It's like if you throw a die and you throw a coin, the probability to get a head or a tail doesn't depend on the result of the die. Or the probability to get a 6 doesn't depend on if the coin ended up as a head or a tail. They are independent. So these formulas are by definition. They must be true. Let's now look at the formula we worked with over here. The probability for A to happen, given that B has happened, is equal to the probability for A happen and B to happen divided by the probability for B to happen. And we know that say with these two events are independent, and then we know that this part must be equal to the probability of A. Given that these two are, let's say, if independent, then this must be true. So in other words, we can say that the probability for A to happen equals to probability for A to happen and B to happen divided by the probability for B to happen. Just replace this. Since they are independent, the probability for A to happen shouldn't depend on the probability for B. On this formula, we can now multiply both sides by the probability for B. I use the symbol for do this on both sides. So we get this formula, the probability for A to happen times the probability for B to happen equals to the probability for A intersection B to happen. And this is true if this is true. It's the same thing that the A and B are independent. So if A and B are independent, then this will be true, and if this is true, then A and B are independent. So this will make us a test for independence. We can of course use this and that, but quite often this is the easiest way to test it. So let's check the case we have over here. Is that are these two events independent or dependent? So what we do is we take the probability for A and multiply that by the probability for B. And that will in this case give us 0.5 times 0.7, and that is equal to 0.35. We also know that the probability for A to happen and B to happen, the intersection, equals to 0.3, and 0.35 is not equal to 0.3, so A and B are not independent. The two cases, the two events are dependent. That is a way to use that. Okay, so let's look at a problem where this could be used. Say we have two events, A and B, and they are independent. I can't write here, sorry. Independent doesn't. Okay, it will be good enough for now. And say we have this information that the probability for A to happen but not B is 0.1. The probability for B to happen but not A is 0.4, but we don't know the intersection here. And we don't know the probability for neither of these to happen. So the question could be find x and y. So they are independent, which means that we can use this formula, and the probability for A is 0.1 plus x, right? This is the probability for A to happen, times the probability for B to happen, which is 0.4 plus x. That is the probability for B to happen. And that should be equal to the probability for the intersection to happen, which is x. That is the probability for A intersection B to happen. So we have an equation. We can expand this. The 0.1 times 0.4 is 0.04 plus 0.1x plus 0.4x, right? 0.1 times x, 0.4 times x, time plus x squared, right? X times x equals to x. We can rearrange this so we get a more ordinary quadratic equation. X squared plus 0.5x, right? Minus 0.04 equals to x. We can subtract x from both sides and get equation x squared minus 0.5x plus 0.04 equals 0. And we have a quadratic. Of course, if this would be this would be done without calculator, we can solve this quadratic using quadratic formula or something. But say, make life easier for us and say we have a calculator, so we can go to some kind of equation solver. We have a polynomial solver here, second degree, and we enter our values: 1, negative 0.5, and 0.04. Solve, and we get that x here is either 0.4 or x equals to 0.1. And of course, if we know that x is 0.4, we have 0.4 plus 0.4 is 0.8 plus 0.1 is 0.9, so y must be 0.1, right? Because 0.4 plus 0.4 plus 0.1 plus 0.1 is 1.0. And here we can find that y is 0.1 plus 0.1, 0.2 plus 0.4 is 0.6, and 1 minus 0.6 equals to 0.4. And we have found our solution here, right? Let's say or. So either this is true or that is true. Okay, let's double check that these depends are really independent now. So let's draw this diagram again, but now with values. Say for this situation, we have that this is 0.1, this is 0.4, and this is 0.4, and this is 0.1. A and B. So what is the probability for A to happen given that B has happened? What is the probability for A to happen given that B has happened? Now we resort back to this formula. We will get that it's 0.4 over the total there, which is 0.8, and that will give us a probability of 1/2. But what is the probability for A to happen? Oh, 0.4 plus 0.1 is 0.5, so indeed we have 1/2. And in a similar way, you can check that B is independent, so to speak, from A, and the same way you can do with this to verify that these two now are actually independent events, given that x is either 0.4 or x is 0.1. I hope this helped a little bit. Thank you.